Hello, yes, sir. Can you hear me? Thanks for coming. We're gonna wait for a few more minutes in case somebody joins. We'll continue. So yes, sir. Are you with me? Can we get started? Perfect. Let me find what we're gonna do today. Oh, yes, sir. I suggest we practice on using rates of change to create certain graphical models. In a previous class, let me start from beginning. It's going to be recorded, so you want a smooth cut. Hello, guys. Welcome to Advanced Function Grade 12 classes. Thanks for coming to the class. And in the last class, we finished instantaneous rate of change chapter. You'll have a chance to ask any question if you still have any. So in today's class, we're going to cover next unit. We're using rates of change to create a graphical model. And then we'll dedicate our time to problem solving of units we covered so far. The goal of today's class is to represent verbal descriptions of rate of change using graphs. Learn about the math. Today, Steve walked to his part-time job. As he started walking, he sped up for 3 minutes. Then he walked at a constant pace for another 2 minutes. When he realized that he wouldn't be early for work, he slowed down. His walk ended. His walk ended, and he came to a complete stop once he reached his destination 10 minutes after he started. What would the speed versus time graph of Steve walk to work look like? So, Yasser, first thing first, in order to create a graph, what do we have to do? We have to plot the coordinate axis. Simple as that. Without coordinate axis, we cannot make any graph. XY, or in this case, as soon as Steve is walking to his part-time job, so one of the variables should be his speed, and the other variable is the time that he spent. So x-axis would be my time, and y-axis would be my velocity of Steve with respect to time. Is it understandable? So, moving on, let's analyze data that we have. As he started walking, he sped up for 3 minutes, then he walked at a constant pace for another 2 minutes. So when he started walking when the time was equal 0, as well as the speed. And he was speeding up for 3 minutes. 3 minutes time frame is here. 3 minutes. He was speeding up. And now we have to decide. Remember, when we talk about rates of change, we could have a constant rate of change like linear function. And other functions like quadratic may not have constant rate of change. Okay, but let's assume that Steve was speeding up with the linear dependence. He was like increasing his speed per 1 kilometer every minute. So we would have a straight line going up to moment of time of 3 minutes. Then after this point of time, for another 2 minutes, he walked in a constant pace. So he sped up and then he kept this rhythm. So here we're gonna have 2 minutes time frame, which makes this point 5 minutes. In this time frame, he was walking in a constant pace. So our graph won't change, right? The velocity is not supposed to change if somebody walks in a constant pace. So Yasser, can you tell me what would be the rate of change in this time interval? Yasser, are you paying attention? So here we plotted the graph for Steve walking to his job, where his first time period is him accelerating. Meanwhile, second time period is him walking in a constant speed, and the third time frame when he was decelerating and decelerating up till the moment when he reached his job. Here is the drawing the book suggests us. Everything is same. Here's second solution. In this case, we assume that he was not speeding up with a linear dependence. For example, what if he started running, and when you run, you accelerate even faster, faster, faster. So in this case, the rate of change won't be constant. And you won't get a straight line. The rate of change would be something different. But still, the average rate of change from the start of the axis to the point in time where he starts moving at a constant speed, the average rate of change should be roughly the same. Which details in the given description were most important for determining the shape of the graph? As for me, the most important thing that gives us 100% certainty about how the graph looks like was the statement that Steve was walking at a constant rate of change in a moment of time after 3 minutes for 2 minutes, which makes us draw the straight line independently from whether he was decelerating with exponent or in linear dependence. Example 2, representing the situation with a graph. A flask, a beaker, and the graduated cylinder are being filled with water. The rate at which the water flows from the tap is the same when filling all three containers. Draw possible water level versus time graph for the three containers. So draw possible water level versus time graph for three containers. Let's read it once again. A flask, a beaker, and the graduate cylinder are being filled with water. The rate at which the water flows from the tap is the same when filling all three containers. So we fill up all three containers and we fill them up at a constant speed. So tap water is coming out at the same velocity. Okay. But how are we going to describe the water level versus time graph for three containers? So water level is how much water we got in our container. So we would have a so we're gonna have a coordinate axis. And we're gonna have time axis as well as the height axis. It's gonna be h, and it's gonna be expressed in centimeters, while time expressed in, let's say, seconds. So draw possible water level versus time graph with the three containers. I'll use one graph for all of them. The blue one would be this flask. The yellow one would be this one small beaker. And the red one would be this long graduated cylinder. So let's sketch a graph for the flask. As soon as the rate at which tap water enters the flask is the same at all time, so the rate of change should be constant for the height in the flask, isn't it? But no, let's take a look at the flask. We can see that the flask is more wider on the bottom and getting less wide to the top. So it means that we need more water on the bottom to reach certain height than we need water on the top. So at first, it will take some time for us to fill up the flask at this level, but then it's gonna take fewer time every time in order to fill it up. So my graph, oh, and one more thing, the rate at which my flask is filling up is increasing. So I'm gonna have an exponential dependence, which is not like this, but instead like this. This is moment in time where my flask is fully filled up. Now let's take a look at the beaker. As soon as it's straight, but it's pretty wide, it's gonna take the rate of change at the rate at which the beaker will be filled up is going to be constant, because you see the area that we are filling up with water is constant everywhere, and the tap water comes out constantly. So it will take some time for it to fill up, but again, the graph would be linear, and it would be somewhere here, because we can see that it's 2 times shorter than the flask. So this is where it will be filled up, and until that moment, it will be filling up at a constant rate of change. And finally, the graduated cylinder, we can see that the area is much smaller than for 2 previous containers, and it's much longer. So if we are pouring in liquid at a constant rate and we have constant area, it means the rate at which we're gonna gain height is constant. But for this guy, we're gonna gain height much faster because area is smaller. So our graph would look something like this. Where's the red line where we fill up the graduated cylinder completely. And you can see here the 3 graphs they suggest, and luckily my graphs same with their graphs. Please take a moment to note down this drawing, and please read their reasoning about their graphs, compare it to what we discovered together. So, Yasser, any questions? I'll treat that as no. Example 3. Example 3. Using a graph to determine the rate of change. The cyclist is observed moving at a speed of 10 meters per second. She begins to slow down at a constant rate, and 4 seconds later is at a speed of 5 meters per second. She continues to slow down at a different constant rate and finally comes to a stop 6 seconds later. Sketch a graph of speed versus time. What is the average rate of change of the cyclist's speed in the first 4 seconds? Estimate the instantaneous rate of change in speed at 3 seconds. The cyclist is observed moving at a speed of 10 meters per second. For this type of problem, no need to sketch the negative part of t-axis as soon as time don't go to negative usually. Here's the velocity. So cyclist is observed moving at a speed of 10 meters per second. It means that his speed at the moment when we start observing him was 10 meters per second. Velocity meters per second. So the cyclist begins to slow down at a constant rate and 4 seconds later is at speed of 5 meters per second. 4 seconds, 5 meters per second. So we would have a nice straight line. I'll use green color. From 10 to here, where 2 other points meet. 4 seconds, 5 meters per second. She continues to slow down at a different constant rate and finally comes to a stop 6 seconds later. So 6 seconds later means a total of 10 seconds should pass for her to come to a complete stop. And we also know that she's slowing down at a different constant rate. Now let's assume that this, let's take a look whether this rate of change should be more steeper or less steeper, whether she slows down faster or slower. Look, here in 4 seconds, she slowed down for 5 meters per second. And next period of time, in 6 seconds, she slowed down for another 5 meters per second. So I make a conclusion that from 10 to 4, she was slowing down more intensively than from 10 to then from 5 to 0 or from 4 to 10. Okay, we sketch the graph. What is the average rate of change of the cyclist speed in the first 4 seconds? So average rate of change in this moment of time, we can use our well-known formula, delta V of t over delta t, where 2 moments of time 0 seconds and 4 seconds. So at 0 seconds, our speed was 10 meters per second, and at 5 meters per second, it's 4 seconds after. So it will be 5 minus 10. We subtract the beginning from the end. So it would be 5 minus 10 divided by beginning from the end, 4 minus 0, which gives us -5 divided by 4. -5 divided by 4. And this would be our average rate of change for the period of time from 0 to 4 seconds. And take a notice that we have negative rate of change, which means we were decelerating, which corresponds with the task, with the problem that we're given with. So we're right. This would be the average rate of change. Estimate the instantaneous rate of change in speed at 3 seconds. 3 seconds were before 4 seconds. And what is the instantaneous rate of change in speed at 3 seconds? And it's quite easy to answer because according to the task, we know that the cyclist began to slow down at a constant rate, and she was slowing down at a constant rate all the time from 0 to 4 seconds. So logically, instantaneous rate of change would be equal to average rate of change in this period as soon as it's linear dependent. And it would be -5 divided by 4. Here's my solution. Please take a look at the solutions they suggest you here. Let's take a look. Please take a moment to copy down the solution into your textbooks and we'll get moving. So I hope you copied down the solution. We'll move on now. Here, it's funny that they still had to do the calculation to verify that the slope would be the same for a moment of time 3 as for from 0 to 4. Okay. Let's solve example 4. And after that, you'll have a time to do your home assignment and practice tasks and ask any questions that you have. Adam and his friend are testing a motion sensor. Adam stands half meter in front of the sensor and then walks 4 meters away from it at a constant rate for 10 seconds. Next, Adam walks 1 meter toward the sensor for 5 seconds and then wait there for another 5 seconds. And we have a whole set of questions. Draw a distance versus time graph for Adam's motion sensor walk. Let's start with that. Again, we don't need negative time. We're just going to use positive time and positive distance. Distance in meters and time in seconds. So Adam stands half meter in front of the sensor. So if this is the scale for distance, let's say this would be 1 meter. So half meter is here. So we start at moment of time 0, half meter away. So this would be our starting point. Then walks 4 meters away from it at a constant rate for 10 seconds. So 0 seconds, 10 seconds, and we walk up to 4 meters away. 2, 3, 4. 4 meters. So our graph would meet somewhere here, in this point. And we also know that he walks away at a constant rate of change. So we have a linear dependence. Next, Adam walks 1 meter toward the sensor for 5 seconds. So then he spent 5 seconds to walk 1 meter back. So 15 seconds, moment in time. And he walked only 1 meter back. So walked to 3 meters, right? 3 meters away from the sensor. And this point would be right here. Again, we don't know whether he walks at the constant rate of change or he doing it in some other way. We'll assume that he's doing it as well as he was walking away from the sensor. He's walking to the sensor with the same constant rate of change. And after that, he waits there for another 5 seconds. Waits there means his distance from the sensor remains the same, so constant for 5 seconds more. Here is the 20 seconds moment in time. And we finally have this graph. It looks similar to what they give us in the textbook. What is the average rate of change in his distance in the first 10 seconds? So to evaluate it, I would have to take the starting point and the end point, 2 and 1, and write down the average rate of change formula, where delta distance over delta t equals, from the end we subtract the beginning. So we would have 4 meters, subtract 0.5 meters, divided by a difference in time, it's going to be 10 seconds. So we're going to have 3.5 divided by 10 equals 0.35 meters per second. This would be average rate of change for Adam in the first 10 seconds of his sensor test. What is the instantaneous rate of change at moment of time t1 and t7? Again, considering that Adam stands in half meter in front of the sensor and then walks 4 meters away from it at a constant rate for 10 seconds, you can make a conclusion that the instantaneous rate of change in moment of time 1 and 7 seconds would be equal to the average rate of change in this interval. We can also do that by using the shrinking interval formula or anything else. But if you take any 2 points on this straight line, they would have the same average rate of change as this whole line altogether, because it's linear dependence. It would be different if we would have some kind of exponential dependence here. What is the average rate of change in the next 5 seconds? Next 5 seconds, so from 10 to 15. From 10 to 15, delta d over delta t. So from end we subtract the beginning. 3 subtract 4 meters divided by 15 subtract 10. So we walked for 5 seconds of total, minus 1 equals over 5. Or in other words, and negative 0.2. This is the average rate of change for him in the following 5 seconds. Take a notice that the rate of change is negative, so it means he walks backwards, back to the sensor. What is the instantaneous rate of change at T12 and T14? Again, same reasoning about the instantaneous rate of change. If the average rate of change is constant over the whole time period, the instantaneous rate of change would be as well. And what is the instantaneous rate of change at T18? To do that, let's take 2 moments of time, 18.1 second and 17.9 second, somewhere close to the second value, and evaluate the instantaneous rate of average rate of change for those 2 points. So from in the moment of time 18, we can see that this is the moment where he was not moving at all. So he wasn't changing his distance. So we can say it was 0 here. Or we can say that the distance for moment of time 17.9 and 18.1 is the same. And divided by 18.1 subtract 17.9 equals 0 divided by 0.2. And fun fact, the average rate of change would be 0 meters per second, as it was said in the question. For the next 5 seconds, Adam remains still. He's not moving anywhere. So that makes it reasonable to have zero rate of change. Draw a speed versus time graph for Adam's motion sensor walk. Okay, let me clean this right-hand side. And make a coordinate axis. But here we would have negative, we could have negative velocity here, because at some moment of time, oh no, speed versus time, not distance. So again, speed would always be positive for us. Velocity with respect to time, and here's the time. Speed versus time graph. So we know that from 0.5 meters to 4 minutes, meters, sorry. So from 0 to 10 seconds, Adam walks away at a constant rate. So it means he walks away with a constant speed. Let's assume, and we know the speed actually. Look here, it's 0.5 meters per second. So let's say 0.35 meters per second would be somewhere here. So from a moment of time, from t0 to t10, we're gonna have constant speed. Be constant. From 10 to 15, we're gonna have a different rate of change, and I believe it was I believe it was negative 0.2, right? Negative 0.2 meters per second. But even though we see the rate of change is negative, it doesn't mean that the velocity would be negative. Negative rate of change for this function only means that we walk towards the sensor. While here, by modulo, velocity would remain positive. So if it's 0.2, it was like this, just a straight line, because constant speed. And after that, Adam walks backwards at a lower speed, only for 5 more seconds. But he walks at a constant speed again. So basically, in real life, he would have to slow down a little bit at some rate. But in this problem, he starts to walk instantly at the new speed for another 5 seconds. And then he remains still for another 5 seconds. So finally, his speed for the rest of 5 seconds would be 0. Let me use red color. So first interval, 0.35 average speed. Second interval, 0.2 average speed. And then finally, 0 meters per second speed for another 5 seconds. And you can see, I'm going to clean the left-hand side of my drawing. I'm going to take a look at what they say in the textbook. And here's the graph for velocity over time. And you can see that I was completely right. Right, they say 0.4 meters per second. Oh, here, this is where I made a mistake. They say, and then walks 4 meters away from it at a constant rate. So 4 meter plus 0.5, I'm not sure, it's not so important. But the general idea, I hope you get it in this problem. Please take a moment to copy down the solution. I hope you already have the graph. Just take a look at the approach, how to evaluate the average rate of change. Is there any questions about this particular example? Speed is non-negative quantity, important to notice. And the summary, the key ideas. In a problem that involves small movement, a possible graph shows displacement, distance, height, or depth versus time. Distance, height, or depth is the dependent variable, and time is the independent variable. The rate of change in these relationships is speed. Speed is change in displacement over change in time. On a displacement, distance, height, or depth versus time graph, the magnitude of the slope of a second line represents the average speed on the corresponding interval. The magnitude of the slope of a tangent line represents the instantaneous speed at a specific point. As a result, observing how the slopes of tangent lines change at different points on a graph gives you insight into how the speed changes over time. What you need to know when the rate of change of displacement or speed is constant, you can see that here we're constantly moving away, and here we're constantly moving backwards. An increasing line indicates that displacement increases as time increases. A decreasing line indicates that the displacement decreases as time increases. And finally, horizontal line indicates that there is no change in displacement as time increases. Please take a moment to copy this down into your textbooks. And we'll move on to your practicing home assignment. So I hope you have this information in your copybooks. When the rate of change of displacement or speed is variable, an increasing curve indicates that displacement increases as time increases. You can see that the slope of a tangent line becoming more steeper with respect to time. The speed is increasing as the time increases. The speed is decreasing as the time increases. And finally, the speed is decreasing as the time increases, and the speed is increasing as the time increases. Here we're moving away faster, here we're moving closer at less speed, here we're moving away at a faster rate, and here we're moving closer at slower rate. So please take a moment to solve these easy problems, check your understanding, and then I'll open up your here, these 4 problems. Solve them now, and then I'll move on to your home assignment. Okay? So, yes, sir, how's it going? Do you have any questions regarding this problems? I'll treat this as no. And here's the home assignment practicing problems. Please start with 7 to 9. 7 to 9. If you have any questions, please feel free to ask me. So how is doing, guys? Any questions? How's it going, guys? Any questions so far? I believe it's enough time to solve these problems, no? Let's take another 5 minutes and then we'll see. So guys, I believe I gave you enough time to solve these problems. Let's move on to the final 3 problems. Please start solving. In case you have any questions, feel free to ask. And we'll see how you do this. Yes, sir. Have you done the assignments? The exercises? Anyway, I'm going to solve 11 and 12 with you together. Just an example. So, a cross-country runner is training for a marathon. His training program requires him to run at different speeds for different lengths of times. His program also requires him to accelerate and decelerate at a constant rate. Okay. Today he begins by jogging for 10 minutes at rate of 5 miles per hour. So let's see the question. Make a speed versus time graph to represent the situation. So let's sketch the graph right away. This is my advice to you on how to solve problems effectively. When you read it, start noting down information right away. This will save you lots of time. So we have time, a speed versus time graph. Speed represented as v, velocity, and we can see that it's miles per hour in this. And miles per hour the speed, and 10 minutes the time. So time will be in minutes, and velocity in mile per hour. Okay. He then spends 1 minute accelerating to a rate of 10 miles per hour. Okay, today he begins by jogging 10 minutes at a rate of 5 miles per hour, and he's required to accelerate and decelerate at a constant rate. So for 10 minutes, he's running 5 miles per hour. Let's say 5 miles per hour would be this point, and 10 minutes would be this point. So for 10 minutes, from 0 minutes, he's running at a constant rate of 5 miles per hour. Then spends 1 minute accelerating to a rate of 10 miles per hour. 10 miles per hour, gonna be twice as much before. So 10 miles per hour, and he spends only 1 minute to accelerate. So we split up in 10. If we split it up in 10, it would be roughly really close, only 1 minute time frame. So I can also say delta t equals 1 minute. If in 1 minute he accelerates to 10 miles per hour. Following point. And delta t only 1 minute. So here's the moment of time, 11 minutes. He stays at this rate for 5 minutes. So for 5 minutes, he's gonna run at a constant rate of 10 miles per hour. Delta t equals 5 minutes. So this would be 15 minutes. He then decelerates for 1 minute to a rate of 7 miles per hour. He then decelerates for 1 minute to a rate of 7 miles per hour. Again, delta t be equal 1 minute and he decelerates to 7 miles per hour. Miles per hour. Connecting these 2 points. Again, moment of time is 16 minutes, 1 minute after previous point. He decelerates to 7. Let's join those 2 points. He stays at this rate for 30 minutes. So 16 plus 30 would be 46. And he stays at that rate for that long time. We join this point, so it would be just constant horizontal line because he's not changing his speed. His rate of change is 0. So the slope of a secant or any tangent line to this curve would have a 0-degree angle. Finally, to cool down, he decelerates for 2 minutes to a rate of 3 miles per hour. What an incredible runner. He's cooling down while running. He stays at this rate for a final 10 minutes and then stops. So he stays at this rate for 30 minutes, finally to cool down, he decelerates for 2 minutes to a rate 3 miles per hour. 2 minutes, he's decelerating. So again, delta T would be 2 minutes now. So moment of time 48, right? 2 minutes after 46. And he decelerates to 3 miles per hour. 3 would be here. I'll zoom out a little bit so we can see the graph more clearly. Right. He stays at this rate for a final 10 minutes and then stops. 10 more minutes, he stays at this rate, so moment of time, 58 minutes. And after that, he finally stops. And let's say he stops instantly. Or is that possible? You should know that in reality, there are no processes that can behave like a non-function. For example, have 2 y values for the same x value. So in reality, this runner would decelerate gradually. He will spend some time in order to stop. That's why any car has a braking distance, because it's impossible to bring your energy to 0 in no time. So that's why there are functions and there are such things as no function. For example, when we have just vertical line. So then he stops in some short period of time. Make a speed versus time graph to represent the situation. Please take a look at the graph I made with you. I think it's pretty clear. So let's repeat it one more time. He is required to accelerate and decelerate at a constant rate, so which tells us the lines in moments of times when he is decelerating or accelerating are supposed to be constant, like, or lines, straight lines, no curves. So the program requires him jogging at a constant rate. He begins 10 minutes by at a rate of 5 miles per hour. This is exactly what we can see in the first block right here. I'm going to use some other color to highlight it. Let's say red one. No, let's use purple. So in this area, he was running constantly at the rate of 5 miles per hour for 10 minutes. Then he spends 1 minute to accelerate to a rate of 10 miles. This is the moment of time. Then he stays at this rate for 5 minutes. This is what we have here. Then he decelerates during 1 minute to 7 miles per hour. He stays at this rate for 30 minutes. Finally cooling down, decelerates for 2 minutes to a rate of 3 miles per hour, then runs 10 more minutes and stops. Great. What is the instantaneous rate of change in the runner's speed at 10.5 minutes? So we're interested in 10.5 minutes period of time when he was accelerating from 5 to 7 miles per hour, from 5 to 10 miles per hour, sorry. And we can see that our rate of change is constant over this period of time. So the instantaneous rate of change would be equal to the average rate of change in this period of time. So when t equals 10, it's t1, and velocity v1 equals 5, and t2 is 11, and v2 is 10. Now we write the average rate of change formula with these two values, and we can see that we're going to get 10 minus 5 divided by 11 minus 10, which gives us 5 divided by 1, or just 5. And what quantity is this? It's a rate of change of velocity, and that's what's called an acceleration. And acceleration is calculated in meters per second squared, because velocity is meters per second, right? And time, we divide by time again, and time is seconds. And we have to note down one interesting thing. We cannot just take 5 miles per hour and 10 miles per hour and use them with minutes. We have to convert the minutes into hours. Or shouldn't we? In reality, what we're discovering right here is the properties of the function, right? So if we convert the time to hours, then we could say that it's miles per hour squared, like acceleration. But if we keep it as is, we're just going to get a quantity which describes miles per hours per seconds. So what acceleration we get with respect to, oh, sorry, not seconds, but minutes, because in this problem, we're describing the periods of time in minutes, you see? So we basically would get a rate of change of the function where velocity as some integer or quantity depends on time with respect to minutes. So it won't be a problem for us. So here we get rate of change of 5 miles per hour per minute. And that's reasonable because here in 1 minute, we accelerate from 5 to 10 miles per hour. So our rate of change is 5 miles per hour per minute. You can convert this answer and find the answer in miles per a minute squared. That would be a bit different number. So we can state that instantaneous rate of change in the runner speed at 10.5 minutes of time was 5 miles per hour per minute. Calculate the runner's average rate at which he changed speed from minute 11 to minute 49. So now we have to use the same formula, but just replace values. Average rate of change speed from minute 11 to minute 49. So 49 minus 11, and let's take a look at 11 minutes, his speed was 10 miles per hour. So, and 49, he was running constantly at a speed of 3 miles per hour. So we subtract 10 from 3. He was running at a speed of 10 miles per hour. It's V1 in this case. And at moment of time, 49 minutes, he was running with speed of 3 miles per hour, or V2. So we get -7 divided by 38, which tells us that he was mostly decelerating in this period of time. And because the second point is lower on the graph than the first point, the average rate of change basically decreasing. If you draw a straight line that joins these 2 points, it's a second line, right? And we can see that the angle is negative, right? If we look in the circle, coordinate, this side is positive, this tangent would be negative. So we can make a statement that he's decelerating. Explain why your answer for part C does not accurately represent the runner's training schedule from minute 11 to 49. It does not represent the answer accurately, because during these periods of time he was decelerating at a different rate of change, and furthermore, at certain periods of time, he was running at a constant speed. So we cannot say that he was constantly decelerating from one point to another. It just describes the general behavior of a function between these 2 points. Is there any questions about this problem? Oh, one more thing. You can see that according to this evaluation of the average rate of change, we can see that he is decelerating very slowly, because if -7 divided by 38 is it's a fracture, right? And it's going to be some decimal places. But in reality, he was decelerating real quick at some moments. Here for 2 minutes, he decelerated from 7 to 3. In 1 minute, he decelerated from 10 to 7. But according to the average rate of change, he was slowly decelerating in this time frame. That's one more reason why our answer cannot accurately represent the runner's training schedule. Okay, guys, I hope you learned something new today, and I hope you practice with these problems during the class time so you can have more time at home. I wish you good weekends. Please check out your Google Classroom for updates, and if you're missing this class, you're gonna see it on YouTube channel. Thank you for your time, Yasser. Have a great weekend.